Hello everyone, greetings from Institute of Aeronautical Engineering and welcome to IARE ELRV course on electromagnetic waves and transmission lines. And our today's topic is Smith chart. This is Dr.Y Pandu Rangaiah, Associate Professor in the Department of Electronics and Communication Engineering. And after completion of this session, the learners will be able to apply the fundamental concepts of the reflection coefficient and also the fundamentals of mathematics for the formation of R and as well as the X circles. And also they will be able to construct the Smith chart from the basics of the reflection coefficient. So in this session, we will cover about what are the R circles and X circles and also the intersection of the R and X circles, which is called as the Smith chart, starting from the basics of the reflection coefficient, and in between we will use the knowledge of the mathematics. Where the Smith chart is a graphic tool to solve the problems in case of the transmission lines, and which consists of the R circles and as well as the X circles, and the Smith chart is the intersection of both the R circles and as well as X circles, which are represented in circular form, where we know that the reflection coefficient, it is defined as the ratio of reflected voltage to the incident voltage, and which is a complex constant, and also that the reflection coefficient is a vector quantity which has both magnitude as well as the direction, and which could be represented in terms of the receiving end impedance and as well as the characteristic impedance by the equation K is equal to ZR minus Z0 divided by ZR plus Z0, where ZR is the terminating impedance and Z0 is the characteristic impedance. Suppose if I divide both numerator and denominator of the reflection coefficient expression with Z0, then it may get it is an K is equal to ZR by Z0 minus 1 divided by ZR by Z0 plus 1. Suppose if I assume that the ZR by Z0 as the normalized terminating impedance, which we will denote with Z suffix small r, ZR by Z0, if I assume it is a normalized terminating impedance, means we are taking that the terminating impedance with reference to the characteristic impedance, and which we will call it is a normalized terminating impedance. Then we can write it is the expression for the reflection coefficient as ZR minus 1 divided by ZR plus 1. Or from this equation, if I solve it, therefore I can write it is ZR equal to 1 plus K divided by 1 minus K also. So here, where the reflection coefficient K is a complex constant, it has both the real and imaginary values. Suppose if I represent that the reflection coefficient as an KR plus JKX, where the KR is the real part of the reflection coefficient and KX is the imaginary part of the reflection coefficient. Since that the reflection coefficient is a complex constant and it is a vector component, it has both the magnitude and the direction, we can represent in the form of the real and imaginary parts, the K is equal to KR plus JKX. In similar way, the normalized terminating impedance ZR, which is also a complex constant, and which we can represent here, if I represent it is an R plus JX, where R is the real part of the normalized terminating impedance and capital X is the imaginary part or the reactance of the normalized terminating impedance. If I represent, then if I substitute these two complex constants in terms of its real and imaginary values in this expression, then it will becomes as an ZR is equal to R plus JX equal to, I can write 1 plus K divided by 1 minus K, 1 plus KR plus JKX divided by 1 minus KR plus means it becomes minus JKX. Now I want to equate the real parts and the imaginary parts on both sides of this equation. So to equate, I want to rationalize on the right hand side term. So I am multiplying this equation with respect to 1 minus kr plus jkx divided by 1 minus kr plus jkx. Then I want to simplify this expression where it will becomes r plus jx is equal to, if I take it is in the numerator, then it will becomes 1 plus jkx, if I take it as an one term, and plus kr, 1 plus jx minus kr, it will be looks like it is an a plus b and a minus b, where it is an a square minus b square minus kr square. I can write the numerator. Similarly, the denominator part, we have 1 minus kr minus jkx plus 1 minus kr plus jkx. That also I can write a square minus b square means jkx whole square. And if I simplify this expression further, then it will becomes r plus jx equal to, numerator if I start to simplify, this is a plus b whole square, a square, that is an 1 plus b square, j kx square, j square is the minus 1 means minus kx square, then it is an minus kr square here, then it is 2jkx plus 2jkx divided by, this is 1 minus, I am writing as it is, 1 minus kr square. If I write the j square is the outside, then it will becomes j square is nothing but minus 1. Then I can write the plus kx square. Now I will equate that the real and imaginary parts on both sides of this equation. Then I may get r equal to 1 minus kx square minus kr square divided by 1 minus kr square plus kx square. And I will call this as an equation 1. And if we equate that the imaginary parts on both sides of this equation, then x is equal to, I will get 2kx divided by 1 minus kr square plus kx square. This I will call it as an equation number 2. Once again I will repeat, and we consider it is the reflection coefficient expression, where k equal to zr minus z0 by zr plus z0. We have been divided with numerator and denominator with z0, and we call the zr by z0 as a normalized terminating impedance, and we find the expression for the k equal to zr minus z1 divided by zr plus 1, where the zr is the normalized terminating impedance, where in this expression the k and zr are both the complex constants. When it is a complex constant, I am writing it is the k zr as r plus jx and k as kr plus jkx, and I am substituting that those two complex constant in this above expression, and I am getting this value r plus jx is equal to equate the real and imaginary parts on both sides of this equation, I am rationalizing that the right hand side term. Then by rationalizing that, where we are getting it is an r plus jx, I am multiplying with 1 minus kr plus jkx divided by 1 minus kr plus jkx. Then by multiplying, by simplifying, and I am equating that the real and imaginary parts of those equations on both the sides. Then we got r equal to 1 minus kr square minus kx square divided by 1 minus kr whole square plus kx square, and I call it as an equation 1. X is equal to 2kx divided by 1 minus kr whole square plus kx square. I got it is an equation number 2. I will say that this equation 1 is the resultant of the family of R circles, whereas the equation 2 is represents that the family of the X circles. If it is a circle equation is nothing but it must be like this, like it is an kr minus something whole square plus kx minus something whole square equal to something whole square, like it is an x minus a whole square plus y minus b whole square equal to some r square. So if it is in this the form, then I can say that it is in a circle equation. So where I am calling this equation 1 and 2 are the circle equations, but by looking like this, it is an exactly, it may not be like it is an in the circle equation form, where we want to convert or we want to do that some simple mathematics for this equation 1 and 2 to represent same equations 1 and 2 in the form of like kr minus something whole square plus kx minus something whole square equal to something whole square. Then I can say that it may be of having what is the center and what is the radius. Therefore, and by varying that those are values of either r or x, and we may get it is a different kind of circles for different values of the r, that we will call it as a family of r circles. And similarly, as the x may be changes, and it will result it is a family of x circles. So for that, let us now, I will consider it is an equation 1 separately and equation 2 separately, and I will see that and how to convert or how to make this equation to write in the form of a circle equation. Let us now consider it is an the constant r circles, or let us consider that the equation 1 where r is equal to 1 minus kr square minus kx square divided by 1 minus kr square plus kx square. Now I will cross multiply this, then r into 1 minus kr square. I will simplify this equation. 1 plus kr square minus 2kr plus kx square means r into kx square equal to 1 minus kr square minus kx square. Now I will write all the kr square terms at one place, where here we have it is an r into kr square, and it is plus kr square minus 2r kr, right, and these are all the kr terms, plus r into kx square plus kx square and equal to 1, and here it is an extra plus r is there. If I send on to the other side, it is an 1 minus r. So I've been written it is an all the kr terms at one place and kx square one place and 1 minus r. Now if I look at it, this equation where I will take the kr square is the common. If I take, it is an 1 plus r minus 2r into kr, plus here also in the kx square I am taking it is an 1 plus r is the common, then it will be 1 minus r. I will divide with 1 plus r on both the sides of this equation. Then I may get kr square minus 2r divided by 1 plus r into kr plus kx square equal to 1 minus r divided by 1 plus r. Now I want to write this equation in form of circle equation. Therefore here, if you look at this equation, this is like an x square minus 2 into x into y, where here the y square is missing, that is r divided by 1 plus r whole square is missing. Therefore, I will add r divided by 1 plus r whole square on both sides of this equation. Then the value does not changes. So, kr square minus 2 into r divided by 1 plus r into kr plus I am adding r divided by 1 plus r whole square here plus kx square equal to 1 minus r divided by 1 plus r plus r divided by 1 plus r whole square. I am adding this term r divided by 1 plus r whole square on both sides of this equation. Then this three terms looks like x square minus 2xy plus y square. Then I can write this as an kr minus r divided by 1 plus r whole square I can write plus kx, nothing is there here, therefore kx minus 0 whole square I can write equal to, if I take it is an here 1 plus r whole square is the LCM, then it will becomes 1 minus r into 1 plus r. It is an 1 minus r square. R square will be gets cancels, or I may get 1 divided by 1 plus r whole square. See that this equation will be looks like as in a circle equation or not. Kr minus r divided by 1 plus r whole square plus kx minus 0 whole square equal to 1 divided by 1 plus r whole square. So this equation looks like it is a circle equation, and whose center is at r divided by 1 plus r comma 0, and the radius is 1 divided by 1 plus r. Understood? Once again I will repeat this. So we consider it is the expression for this, the real parts by equating on both sides of the equation of a reflection coefficient, where we got r is equal to this expression, and we started to simplify this equation, and where to get it is in the form of a circle or perfect square, where we added r square divided by 1 plus r whole square on both sides of this equation to make it is a perfect square. Then by simplifying, where we got the expression is kr minus r divided by 1 plus r whole square plus kx square equal to 1 divided by 1 plus r whole square, and this above equation will be represents that the family of r circles, where this circle is of having the center is at r divided by 1 plus r comma 0, and the radius is at 1 divided by 1 plus r, where what is the r it is here, which is the real part of the normalized terminating impedance, which we assume. So that this is called as a resistance. The resistance will take only the positive values. R will take only the positive values. Now here I will take it is an R equal to, for different values of the positive values of the R. Now I will consider it is the R is equal to 0. Let us I will take it is an KR axis. This is the real part of the reflection coefficient, and the kx axis I will take here. This is the imaginary part of the reflection coefficient. So it is like x axis kr axis, y axis I consider is the kx axis, kr and kx axis. Now r is equal to 0. I will draw a circle of this. If r equal to 0, what is the center? The center is at 0 comma 0. The center is at 0 comma 0. And what is the radius? If r equal to 0, the radius is 1. So if I take it is 1 centimeter here. So then if I draw the circle, then this will be represents r is equal to 0 circle. I consider it is an r equal to 0, and if I draw the circle, then it is of having it is 0 comma 0 is the center, and 1 is the radius. This will becomes 1 comma 0. This is 0 comma 1, and this is it is minus 1 comma 0, like that. So this is an r is equal to 0 circle, and which passes through this the point 1 comma 0 at the positive kr axis. Okay. Now I will consider it is suppose r is equal to 1. If I take r equal to 1, if r is equal to 1, what is the center? 1 divided by 1 plus 1 means it is 1 divided by 2 comma 0, that is 0.5 comma 0 is the center. So 0.5 comma 0 is nothing but here, it is a point. And what is the radius? 1 divided by 1 plus 1, it means 1 divided by 2, 0.5. So from here, this is the 0.5 comma 0. So this is the 0.5 distance, and this is the 0.5 distance, and this may be the 0.5 distance, and this may be the 0.5 distance. If I draw that r is equal to 1 circle, and this is an r is equal to 1 circle. Similar way, if I take the different values of the r, I will get, if I take r is equal to 0.1, and this may be the circle r is equal to 0.1. If I take it is an r is equal to 0.5, and this may be it is an r is equal to 0.5. Or if I take it is an r is equal to 2, this may be the r is equal to 2, and this may be the r is equal to 10, r is equal to 20, r is equal to 50. Suppose if I take r is equal to infinity, then this center will be becomes as an 1 divided by r plus 1 comma 0. If r is equal to infinity, the center is at 1 comma 0, and the radius is If it is an infinity, 0 means 1 comma 0 is the center and 0 is the radius, means the point itself. Or if you see here, all the R circles are passes through a point called as 1 comma 0. All R circles are passes through the point 1 comma 0. This is called as the family of R circles all together for the different values of the R, which is ranging from 0 to infinity, are called as the family of R circles, where it is of having the center is at R divided by 1 plus R comma 0 and the radius is at 1 divided by 1 plus R. Right? So this is about the family of R circles. And all R circles, including R equal to 0 circle or including R equal to infinity circle, and all are passes through this the point at 1 comma 0. 1 comma 0. Right? So these are the different R circles where the outermost circle is called as an R equal to 0 circle and R equal to infinity circle is a point itself. Okay? Where that 1 comma 0 is the center and 0 is the radius. Therefore, it is a point itself. And this is R is equal to 1 circle and which is of having it is a special significance and which I will tell you that in the later case. Right? And which will be passes through the center of the Smith chart. Okay? So these are called as the family of the constant R circles. In similar way, we'll consider that the equation 2, where the x is equal to, that is by equating the imaginary parts on both sides of the equation, we got it is an x is equal to something. We'll consider that the equation 2, we'll simplify it and again that also will put it is in the form of the circle equation and we'll vary the x values and we'll see that what are the different kinds of the constant x circles we get. Now we'll consider the constant x circles, that is, we'll consider that the equation number 2, where x is equal to 2kx divided by 1 minus kr square plus kx square. I will cross multiply it, x into 1 plus kr square minus 2kr in plus x into kx square equal to 2kx. Or I will multiply it all the kr square terms, I will write at one place, x into kr square minus 2kr into x and plus x into kx square minus 2kx. Here it is and plus x is there, I am sending into onto that the other side, that is minus x. Or if I divide with x on both sides of this equation, I may get kr square minus 2kr plus kx square minus 2kx by x equal to minus 1. If this 1 I will bring on to this side, then it will becomes kr square minus 2kr plus 1 plus kx square minus 2kx divided by capital X is equal to 0. And this will be looks like is in a perfect equation where I can write it is an the kr minus 1 whole square. Whereas this is not a perfect equation, where to make it the perfect equation I need to add 1 divided by x whole square on both sides of this equation. If I add it, it may becomes as an kx minus 1 divided by x whole square equal to 1 by x whole square. Now this equation is also looks like is an the family of x circles, circle equation, where that the center of this x circles is at 1 comma 1 by x and whose radius is 1 divided by x. So where it is 1 comma 1 by x is the center and 1 by x is the radius. Now also I can vary these x values and we can draw that the different x circles. But what is the x here? This is the imaginary part of the normalized terminating impedance, which is called as an reactance. Where the reactance will take it is an positive values and as well as negative values are also. Therefore, the x may vary from minus infinity to plus infinity. Now we need to take those values and we'll start to draw that what are the family of constant x circles. And before going to that, and once again I'll summarize it, where we consider that the expression for the x by equating the imaginary parts on both sides of the equation, the reflection coefficient, that expression by equating, and we got x is equal to this expression. We started to simplify it. So to make it is a perfect square, where we added 1 by x whole square on both sides of that equation, and where we got this expression. By looking this expression, it looks like is a circle equation where it is of having its center is at 1 comma 1 by x and whose radius is at 1 by x. So now this equation is of having the center is at 1 comma 1 by x and the radius is at 1 by x, where x being is the reactance and it can take both positive and negative values. When x is the positive, the circles now will start to draw that, and those circles will be lies it is an above the horizontal axis. If I take the x is the negative, the circles will lies that the below horizontal axis. Now we'll start to draw those x circles. Now I will take, this is the kr axis, this is the kx axis. Now I will take, let us assume that the x is equal to 0, I will consider first. If x is equal to 0, the center is at 1 comma infinity. This is the one center, infinity, somewhere else go on. And radius is the infinity. Therefore, it looks like it is in a straight line. This is called as an x is equal to 0, which passes through this 1 comma 0 point. And I will consider it is an x is equal to 1. Let us will see. If it is an x is equal to 1, the center is at 1 comma 1. This is the 1. And if I take here, this is at the center. And the radius is again it is an 1 meter. So it is 1, 1 like this. So means I may get the circle is like this. This is an x is equal to 1. If and it is passing through this the point at 1 comma 0, because of this is the 1, 1 means it is passing through this point. X is equal to 1. This is, if I take it is an x is equal to 0.1, I may get like this. X is equal to 0.1. X is equal to 0.2, I may get like this. X is equal to 0.3. X is equal to 10. X is equal to 20. X is equal to 30. X is equal to 40 like this. Similarly, if I go for x is equal to minus 1, and I will get it is an like this. X is equal to minus 2, minus 10, minus 10, like this. X is equal to minus 0.1, x is equal to minus 0.2, x is equal to minus 0.5. If I draw that the R circles from here, R is equal to this one, it is called as an 0 circle. Therefore, all these things to write it is an, again it is very difficult here. So therefore, instead of drawing it is an all the things here put together, and where we'll write like this. I will consider it is an, first it is an R is equal to 0 circles, and this is an x is equal to 0.1, x is equal to 0.5, or x is equal to 1 circle, or it is an x is equal to 10, 20, 30, x is equal to minus 0.1, minus 0.2, minus 0.5, minus 1, minus 10, minus 3, right? So these are the family of all x circles, where x is equal to, it is an 0.2, 0.5, this is x is equal to 1, and it is an x is equal to 10, and 20 and 50, and if it is an x is equal to infinity, where it is and 1 divided by infinity is the 0 radius, 1 comma 0 is the center, this point. Again it is a point itself that also is passes through the point called as 1 comma 0. Therefore what we observed is all the R circles and all the X circles will passes through the point called as 1 comma 0. So these are all the circles is called as the family of X circles. And if you look at this, where we drawn it is, and this is an R is equal to 0 circles, which is where it is, this is an X is equal to 0 circle. If it is a positive values and which lies it is an above the horizontal axis, where to minimize that the circle to draw that onto this the paper, where we have been up to here, we have been drawn this, otherwise it is a circle, it goes and again it comes back, and we are not drawing that those circles, and we have been again taken up to that the R is equal to 0 circles to minimize it. So this is an X is equal to 0.2, 0.3, and X is equal to, this is an X is equal to 1 circle, and this is an below that it is an X is equal to minus 1 circle, right? And we got it is, and these are family of X circles, where it is of having it is an its center is at 1 comma 1 by x, and whose radius is 1 by x meters. And here also that all the X circles are passes through the point called is an 1 comma 0, right? So now if both R and X circles are combined together, then that it is called as the Smith chart. So that the complete Smith chart is obtained by superpositioning both R circles and as well as the X circles together is called as the Smith chart, which consists of the R circles and as well as the X circles, where it is and the X is above to this the horizontal axis, it is of having a positive reactance, below that it is of having it is a negative reactance, where R is of having only the positive values, and with different values of the positive values, the outermost circle is called as an R is equal to 0 circles, and the remaining are all again R is go on varies, and it will be radius will be very very less, and again it will becomes R is equal to infinity is nothing but it is a point itself. So on the right hand side it is an R is equal to infinity, onto the left hand side it is an R is equal to 0. Similarly here the X is equal to 0 onto the left hand side, and onto the right hand side it is an X is equal to also infinity. So this is about how that the complete Smith chart is obtained and how it looks like. This is the complete Smith chart, and which is of having both superposition of R and as well as X circles, and which here it is R is equal to 1 circle at this point is called as the center of the Smith chart. This is called as the center of the Smith chart. So this Smith chart is obtained and it will be available in your textbooks, and we can take the printout of this, and by using this Smith chart we can calculate very easily of the input impedances, output impedances, or it is maxima voltages, minima voltages, or VSWR, reflection coefficient, all these values without using the calculator. By using the Smith chart we can calculate very easily, which is helpful for us to calculate all these parameters in easiest manner. So to summarize that, where in this session we learned about and how to form a Smith chart by using that the fundamental equations of the reflection coefficient equation, by using that and by using the knowledge of the mathematics, and how to derive that the constant R circles and as well as the constant X circles. For different values of the R we drawn that what is the family of R circles, for different values of the X we drawn that the family of X circles. Therefore the complete Smith chart is the superposition of the two sets of both R circles and as well as the X circles. Thank you so much, and we'll meet again in the next session where we'll discuss about what are the properties of the Smith chart, and also again we'll find out what is an applications of the Smith chart. That we'll discuss in the next sessions. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.